How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to continue working on this medium-sized site, and we're going to talk a little bit about what we're going to go do. Because just like we did in the small site, where we came up with a game plan of how to go after it and tackle that responsibility, we're going to need to do something very similar to that with the medium-sized site. And then when we get over to the larger site here where we got more networking going on, we're going to do the exact same thing. But for this particular site, we're going to be taking it a little bit further. I'm going to be adding in some things that we haven't talked about yet, like VLAN trunking protocol, how that comes into play with VTP. And then we're going to be doing extended range VLANs, because that's another topic we haven't talked about yet. As a matter of fact, we will go ahead and pull over the blueprint real quick. We haven't talked about the extended range VLANs, and we haven't done any manual VLAN pruning. So that is going to be the other thing that we're going to have to dive into and lay out as we get further into this. And then once we get that done, we'll be able to focus on other stuff as we go along. So out of the gate, one of the key things, just like the small site, is we need to come up with a game plan for what we're going to do. So just about every time I've ever had to deploy a decent sized site, there has always been a conversation about the site itself. So, how many users and stuff like that. Some of that stuff is done. I get that information ahead of time. I've had conversations with, the business. I know how many users, the subnets. There's been a lot of planning on the back end when a new site gets deployed, especially a greenfield location, and we're having to do any number of things to get that site up and running. So the idea here is to do, we're going to come up with a subnetting structure, and we're also going to figure out what VLANs we're going to use. We have 4 PCs over here that we need to get talking back and forth. We're going to have, we're going to do the same 4 VLAN design here, over here. And so that takes us to something we talked about briefly in some other videos, that can you reuse VLAN IDs in more than one location? And the answer to that question is you can, right? I can use VLAN 310, 311, 313, and 314 up in this site if I was to choose to do so. Now, I don't like doing that simply out of principle. It's just because you can doesn't mean you should. The coulda, shoulda, woulda kind of mindset. Just because you can do something doesn't mean you should do something. It's more like there's an etiquette that everybody should use when it comes to networking, and you should use good judgment. So I would use a different set of VLANs just because it makes the most sense. Now, what I would do is based off, I'm using the subnet itself to build the VLAN ID. So I can still use the 300 range, right? 315 and so on. I would just have to figure out what particular subnets I'm going to allocate here, and then I can grab a particular part of the VLAN ID, or the subnet itself, like the second and third octet, and then talk about and leverage those numbers to use that as the VLAN ID. So that's essentially the VLAN scope that I'm leveraging, or the methodology. But you could use pretty much whatever you want, right? You don't have to use you could reutilize the same VLANs, but again, I don't think that's a really good business practice. I think it's, or a networking practice. I think you really should come up with a different set of VLANs and different set of subnets. The subnets is the key thing. You don't want to have more than overlapping subnets, because destination-based routing is deterministic. It's deterministic based off of a differentiator. The differentiator is you don't utilize the same subnet in 2 different locations unless you have a mechanism to stretch that particular VLAN between 2 different locations. And an example of how I would do that would be over here in this setup here. What I will eventually do is N73 and N77, they both have a link to a CSR1000V. My goal is to set up a VPLS circuit, basically a point-to-point E-LAN, or an EPL, an Ethernet private line, and I'm going to set that up to where N73 and N77 will be able to talk to each other over that point-to-point /30, and I'll be using BGP to do the interconnectivity. So that'll be something that I leverage there, and then I'll be able to stretch the VLANs that are down here to over here, leveraging VXLAN. But that's the key thing. I'm using something else besides layer 2 networking to extend the VLAN between two different locations. So I'm using VXLAN, and VXLAN extends layer 2 communications over a layer 3 interconnect, or backbone, or fabric, whatever term you want to throw at it. So we'll talk more about that in detail later, but I wanted to specify why I'm doing things the way that I'm going about doing them, because I don't want it to be, well, Rob told me this. Well, Rob didn't tell you to do anything. Rob gave you some guidelines to kind of follow, and that's all I ever do, is I tell you how the technology works and some places you might want to reference it, but it's, most people that watch this content are going to be smart enough to know that, I'm giving you my own personal experience and the factoidal information that goes towards how the technology works. There is no, whenever you're building a network, you must do it this way. That is not the case. So there's enough flexibility in networking that you don't have to follow everything I say. With that being said, we're going to do the same for VLANs. So I'm going to go ahead and I'm going to duplicate this guy. As a matter of fact, let me go ahead and get out of the way. And I'm going to put this guy right here in the middle. And we're going to use different VLAN ranges. So I'm going to click in here. Now, if you notice here, I'm using 172.31.0, 3, and 4 /25. So in total, if I was to come up here at the top and go to the beginning and we're going to have 172.31.0.0 / basically 20 is 16, 21 is 8. So you might ask, how did I come up with that number? So let me do a little bit of subnetting to find the most bits in common to explain how I came up with that. So the answer to that question is actually very simple. So going back to our subnetting content that we went over, remember that we have 8, 4, 2, and 1 are the low order bits, meaning that if we look at the subnets themselves, right, we have 0, which would mean that no bits are turned on. If we look at this one here, this is a 1, so this is turned on. This one's a 3, which means, so a 1, we have actually, take that back. We have a 0. Actually, let me write this over. Let me clear the screen off. So we have a 0, a 1, a 3, a 4, and we need to figure out what 4 /25 is the first half of a subnet, right? It's the first 128 bits. So what I need to do is I need to figure out what the most bits in common are here. So to do that, I'm going to go and say 8, 4, 2, 1. And then I know this is going to be 0. Then this is going to be a 1. This is going to be a 2 and a 1, make 3. And then this one here is going to be a 4. So everything else is zeros, right? So now that we have all that done, if I wanted to include all of these connections, all these subnets into one routing advertisement, which is known as a summary, the way that I do that is I find the most bits in common, and the summary is the opposite, so it is not the same as subnet. Just let me pound on that for a second. If you are subnetting, you're taking a very large amount of IP addresses, /20 or /21 or /16, and you're trying to break that up into smaller networks, or subnetworks. So you're taking that /16, you're breaking that into multiple /24s. So Here I'm doing the opposite. I'm taking multiple longer match, slash 24, slash 23, slash 25, taking longer match subnets, and I'm trying to make them shorter and summarizing them or super netting them. I'm doing the opposite of a subnet. So let's continue talking about that. So because of that, I know in order to encompass all of those, the 4 is, the 4 is essentially where I want that to go. Meaning I need to figure out what a 4 is in the third octet. So if I take 128, 16, or sorry, 128, 64, 32, 16, 8, 4, 2, 1, this is going to be a slash 17, slash 18, slash 19, slash 20, slash 21, slash 22. And I'm able to figure that out because I know everything to the left is going to be A and B. This is going to be a slash 8. This is going to be a slash 16. So if I'm already into the third octet, the first bit is going to be a 128, that's 17. So 16 plus 1 is 17. So my subnet would be 255.255.128. So because I know I'm dealing with a 4, right, and the 4 is here, so I take all these numbers right here and I add them all up, all the way to this guy. So I take 128 and 64 is 192, 192 and 32 is 224, 224 and 16 is 240, 240 and 8 is 248, 248 and 4 is 252. So my subnet is going to be 255.255.252.0. That is going to be that, which is going to be a slash 22 mask, which means I need to make this a 22. So that'll be my advertisement. So that means that'll give me 0 through 4, which means I'll be able to start from a subnetting perspective. I'll be able to start at 5 through 255 is where I'll be able to go with that. With that being said, let's go ahead and I'm going to go ahead and update this guy. Give you a slash 22. And then I will take this guy here and I will come in here and say 172.31.5.0 slash and then whatever I want to come up with. So that 5 is going to be the beginning range. So I'm going to say it'll be another slash 22 because I'm going to have this right here will be a 5. This will be a 6. This will be a, so I did a 5, a 6, 6, 7, this will be an 8, and this will be a 9, slash 25. So now that I've got that, I'm going to move this up a little bit. Oops. Just like that. So now that I've got that figured out, I know what my subnet range is, right? So now I'll go ahead and I'll update this. This will be a 5. This will be a 6. This will be an 8. And this will be a 9. Right? So there we have that. So now we've got all that figured out. We can move on. So I figured out my subnetting. And then I figured out my summary. So now that I've got that done, I can go ahead and begin moving forward with the next step. Now, we haven't talked about VTP, VLAN Trunking Protocol, but I'm going to go ahead and do that now because even though it's not on the blueprint, I'm still going to talk about it because it's still out there. I'm not exactly sure to what extent people use it anymore. No customer of mine in the past several years leverages VTP, but it's not even on the blueprint. But I'm going to talk about it anyway because you might run into it, and it's something that is out there. It's commonly deployed on switches today. It's a feature, but I don't know if people, at least in my experience, no one really uses it. So what is VTP? So let me come down here and we're going to whiteboard this out for a little bit. And I'm going to go ahead and get out of the way. So VTP stands for the VLAN Trunking Protocol. And you might ask, what exactly does that mean? What this means is it really should be replaced, trunking should be replaced with VLAN. Sorry, I just had the word on the tip of my tongue. Replication. VLAN replication protocol. Well, what do I mean by that? Well, what I mean by that is this. If I have switch 1, if I have switch 2, and they're connected to each other, and let's say I've got 28 devices attached to this switch, and of that 28 devices, I've got 6 VLANs. Let's say we've got 10, 11, 12, 13, 14, and then 15. And then, so we have an even distribution, so we've got a number of devices, per VLAN. It doesn't really matter. Figure 28 divided by, actually, let's make that a 7 for simple math. Make this 7, and then we're going to go, this will be 16. So we're going to have 4, in every VLAN there's going to be 4 devices across the board. So we'll just, across the board there are 4 devices per VLAN. Simple math, right? Well, what would end up happening is, in a normal scenario, if I wanted to extend VLANs between switches, I'd have to go to every switch and create all 7 VLANs here and all 7 VLANs here. Well, in reality, that's actually what you want to do. But let's say, for devil's advocate and for the sake of argument, let's say that we wanted to make it easy. We wanted to create the 7 VLANs in one place and have that information pushed out to the rest of the network. How would we do that? And the answer to that question is going to be VTP. That is what VTP's job is to do. There are 3 modes of VTP. You have server, you have client, and then you have transparent. Server is a add, edit, delete capability. So you can add a VLAN, you can edit it somehow, the name change it, whatever, and delete the VLAN. Client means that you only receive updates. He's a receiver of information. Let's put here, receive updates. And then transparent is you're a rebel, right? You do not listen to, so passive. If you want to create VLANs on the transparent VTP enabled device or a transparent mode device, you have to go to that device, just like I mentioned here a moment ago. You have to go to that device individually and then create the VLAN there as you're going along. So when we do that, it gets the job done. So if I'm here and this guy is the server and this guy here is the client, if I create a VLAN on switch 1, let's say I create VLAN 10, after a couple of seconds, VLAN 10 through a VTP update is sent down to switch 2. Switch 2 gets it. Now switch 2 also has VLAN 10 created on it. And then all I have to do is go to switch 2 and, let's say, for example, in ports 1 through 4 is VLAN 10. And then you got, so on and so forth. Then I get a notification I need to create VLAN 11. So I create VLAN 11. VLAN 11 gets pushed to switch 2. VLAN 11 is here. And then I add ports 5 through 5, 6, 7, 8. So I add ports 5, 6, 7, and 8 into VLAN 11. And then the process repeats itself over and over and over again as far as you want. Now, I'm going to take a step back in time about 9 years ago when I worked for a customer where they leveraged this same design. And I'm going to talk about this because it's relevant to the discussion of why you don't use VTP. So this customer had a very large environment. They basically had it was a multi-tier environment, and we'll say that they had DC1, they had DC2, and then while I was there, they added a small DC3. Even though DC3 was supposed to be the same size as DC1, or I'm sorry, DC2. So in between these DCs, they had 6500s. So they had 6509 here. That's a horrible way to write it. They had 6509, 6509, and 6509. Let me go ahead and get out of the way. So they had all these switches set up, and there was two of them. They had times 2, times 2, times 2. So they had two 6500s in each data center. And this was their distribution block. Their distribution block was here. And what they would do is they would downstream of these switches, and these guys were all connected to each other. You'd have a link here, you'd have a link here, you'd have a link here, you'd have a link. They were all connected to each other. So the job got done. It wasn't exactly the cleanest design. And what they would do is they would have access layer switches, 3750, 3850, 2960. You get the point. Each one of these switches would be uplinked to their respective DC distribution block across the board. So they would all be uplinked like this via layer 2. Just like this. And you do 3750, 3850, 2960, so on and so forth. And then these guys would get uplinked to there. Now, what would end up happening is the logic that this particular customer had was, if I plug a server or customer device into this switch here, and I ran out of room in DC1 and I needed to add that customer to DC2 on this switch right here, or actually let's say this switch right here, because they're all connected to this pair of 6509s. What they would do is they would stretch layer 2. So if these were all VTP servers, so you'd have VTP server attached on all of these devices, all these 6509s, and all your access layer switches were in client mode. So what they would do is you would log into this switch right here, and you would create VLAN 321. For example, you create 321. What would end up happening, and this is where VTP is not a great idea, is it would literally push that VLAN to every switch. Every switch. So if you've got, let's say, 80 access switches in this data center, and then you have another 80 in here and another 80 in here, and then you get 6 at the distribution layer, you've got 246 switches all running multiple VLANs. And I think the count before I left working there was 300 plus VLANs. Now we talk about that for just a minute. There is an upper limit to the layer 2 scale on the Catalyst line of access layer switches. On average, for anything that's older model, and I'm not exactly sure what a Cat 9K will support nowadays, but let's just say, for example, a Cat 3K. The last number I remember was 128 VLANs. The reason why there's a number associated to that is because, remember what I talked about, when you create a VLAN, you create a spanning tree instance, and you also create a MAC table. So what ends up happening is if you go beyond this number, you go above 128 VLANs for whatever reason, you're no longer going to have spanning tree instances to protect those VLANs. You're no longer going to have, you're going to run out of MAC address table space if you create that, because there's only so much memory, RAM, which is how the MAC addresses are saved, on each switch. So I remember getting multiple alerts from these switches daily and I had never seen these alerts before. I didn't know what they meant. I had to go look them up. Essentially what they were telling me, they were hardware alerts saying that there was no more space to learn MAC addresses. So the CAM tables, the MAC address tables, the CAM table is equal to the MAC address table. CAM stands for Content Addressable Memory, and it is the ability for the switch to learn MAC addresses. All of this information is real time, and it is saved in RAM, in the onboard RAM of the the operating system is loaded into RAM because RAM is fast. Well, you're loading the MAC address table into RAM as well. So there is an aging timer, but still, you're still being loaded into RAM. Well, what ended up happening was you would end up having all of these switches sitting at between 60 and 80% CPU 24 hours a day, 7 days a week. They had a very short shelf life. I think the average shelf life for a switch in that location was 6 months. Brand new, or like from brand new to the environment, I should say, directly into it would get deployed. It would automatically have a 6-month life, and they would just die. We were replacing switches every couple weeks, and we'd have to pull switches out of inventory. I think we had 30 or 40 of them in inventory, and we were always constantly, not me myself, the leadership of that organization was always constantly hunting on eBay, of all places, to put new switches or to get refurbished switches to keep them in stock, because we couldn't keep them alive long enough because of the way the environment was built. So this is why in a data center environment you don't do campus networking. There are much better ways of doing this. Now I had once I had discovered this and I brought it to management, I was told point blank that the network is a cost center, and that the only way that the organization made money was by selling servers and services. And unless I could make the network a sellable service in some way, then there was no way that they were going to give me any budget to do any upgrades. And so as I was going through and having this conversation, it became, within just a couple of months, this was all discovered. It was an interesting situation to be in. Here I am, CCIE, and this is the network that I inherited, and had been like that for well over a decade. And it was, up to a certain point, it had worked, but they had grown beyond the means and the capability of what this network could support, and were constantly having problems. There was, on a regular basis, there were trouble tickets opened. Now, the reason why I'm going in such a level of depth on this is because VTP was the culprit. So the problem is again, that if you have 321 VLANs, all 321 VLANs are applied to every switch. Now, the reason why that's bad is you have a certain amount of MACs that you can learn. So you have the 128 VLANs, right? But then you also have a limit to how many MAC addresses you can learn. And I forget how many MAC addresses a switch can learn. It should be fairly high, probably a couple thousand if I had to guess based off the memory, because it doesn't take much to save a little bit of information, or to store a little bit of information in real time. But the problem is if I had a device plugged into this 3750, then 6509s and then switches over here, I'll put 3750 over here as well, that were plugged into this guy, would also learn that. Logically, the sprawl made sense, right? Because if you wanted to plug something into DC1 and then plug it into DC3, another device, you wanted anything in that customer's VLAN to work. Okay, it made sense, but the logic made sense. However, the execution was poorly done. Now, I brought up to them doing things like VXLAN and stuff like that, and trying to move away from those things. And I reached out to Cisco, and I was like, hey, I need a quote. I need to replace all this gear, all this other stuff, Nexus 9Ks, Nexus 3Ks, and what can we do to make this better? And I got a very sizable quote back from Cisco, and I said, okay. And this was with discounts. I won't even show you the number because the number was astronomical. It was a very, very high figure. I'll leave you to your own. I don't even remember what the number was because it's been so long, but it was really, really high. It might have been over $1 million. I don't really honestly remember. But with discounts, licensing, SFPs, the whole 9 yards, going from, and the problem with 6509s is they only support 10 gig. The network, we were already stretched beyond that, and we were constantly dealing with bandwidth issues. So, and they were also running EIGRP in the core. So that was a mess all in itself. So in order to fix that, and this goes into the reason why I decided to talk about this, is we were the 3700s, the Cat 3K just couldn't support this. It wasn't tenable. So what I came up with, in the meantime, to try to buy time while I didn't have any, was to be very honest and be like, okay, what we should do is figure out what MAC addresses do an audit on the entire environment. We're going to audit the network. We're going to check on each switch, see what VLANs are actually in use, and then which VLANs are actually applied to access ports. We'll audit per switch, and then once we've done that audit, I will figure out which switch has which VLANs that actually are needed, go up to the distribution layer, and then find out which interfaces those switches are attached to, and then I will come up with a manual prune list, which goes back to our blueprint where we talk about manually VLAN pruning, and then I will allow only those VLANs on that trunk allowed list to go down, to try to limit the amount of flooding that was happening. So I'll do that, and then any VLANs that don't need to be there, I will get rid of them. And then we're going to move away from the VTP server client model, and I'm going to go transparent everywhere. And I was like, it's going to take some time. It's not going to be a disruptive change because the VLANs are still going to, we're going to create the VLANs on a, per switch basis. So we're not going to have a massive, I'm not going to push it through SolarWinds config manager or do like a Python script. I did it manually. I went through and I started going down the path. We started in the smallest data center, which was DC3. We started down that process, and once it was in place, DC3 on its own, because it was new and it was small, it stabilized. We didn't have the issues that we saw in DC1 and DC2, but DC1 and DC2 have been there for years and were fully populated. You couldn't put anything more into DC1 or 2. So when I started talking about that, there was a lot of hesitation from the business because of, there was just an unknown, and they were afraid. They were scared. And I said, I understand that, but we've got to do something. And I said, I'm tired of you guys calling me at 3, 4, 5 in the morning. It happened probably 3 or 4 times over the 6 or so months I was there, where I would get a phone call middle of the morning, or middle of the night, I should say, early AM, because apparently leadership didn't like to sleep because they were that stressed out about the network. And something would be down. And I'd have to wake up. It was about a half-hour drive, so I would always have a VPN access. I'd VPN in, and if I could solve it logically from the house, I would. If not, I'd have to get dressed, drive to the data center, and fix the problem. Which, fortunately for me, other people live closer and were just a couple minutes away and would often handle that, and I'd be on the phone walking them through what to do. Like, okay, you got to go here, download this config, because the switch would die. 3 o'clock in the morning, the switch would just die. And then we'd have a customer calling up saying, hey, my database backup failed, or whatever the case might be. So just in those situations, my goal was to try to help stave off the need to try to stabilize it and go from there. But when I proved DC3 could stabilize, and it did, the CPU utilization dropped down to 20%, because we were still dealing with 20 VLANs and stuff like that, and a fair amount of traffic. So once I got through all of that, I was like, okay, cool, we're on the right track, and I used that as my justification to continue moving forward with the other data centers. But I was met with, well, we're not going to do that because you can't guarantee it's not going to break the network. And I'm like, okay. I was like, even when I would try to argue against it and be like, well, then what else do you suggest we do? Because you've been dealing with this nightmare for longer than I've been here, and no one has come up with a good, solution to fix it. So I was like, and you're not willing to give me any money to go out and buy new hardware, and that was the other thing. Well, so I'm going to talk a little bit about that too. Like, okay, what if we gave you a blank check and said, go buy all the hardware you want from Cisco and deploy your VXLAN fabric? How would you migrate, or how would you get all the stuff that's on the old network to the new network? Excuse me. And I said, simple. And let me talk about that real briefly. So if I have spine 1, spine 2, and if there's a question, am I going to be doing any configuration in this video? No. This is all planning, design, theory, trying to understand how this works and stuff like that. And so no config. The config will happen in the next video. So if I have leaf 1, leaf 2, and leaf 3, what I would end up doing is I would connect this stuff to here, just like this. Going back to the architecture video, doing a spine leaf architecture. And what I would do is connect the old to the new. And how would you do that? Well, let's say, for example, I'm going to put old 1, old 2, old 3, and then I would link these guys together, like this. So they would be connected to the old, and then if anything new came on the network, I would layer 3 connect, I'd connect this stuff to the new, and then it would be connected to the old to be layer 2. So there would still be there on the old. The old and new would still be working in conjunction. The old would be the external network. It would connect out to the outside world until I could move something over to the new. And the way that I said that we would do that is we would focus on customers with a small VLAN footprint, and then I would have a border. So I'll put border leaf 1 and border leaf 2. They'll connect to the spines like so. And what I would do here is I would connect this to 6509s on the edge. So they actually had another layer 6509s up here. So 6509 here times 2, and 6509 times 2 here. One in DC1 and 2 in DC1, 2 in DC2. And the idea was to connect to the outside world. So they actually connected like this, like that. And then so I would connect to the edge, and then these guys would connect out here via BGP. And then from there, if I took the old, let's say I had VLAN 10 was sitting here and was attached to, old 3. Let's say this is DC3. Well, I would take VLAN 10, and then I would have moved, it was layer 2 connected to leaf 3, and then what I would do is I would turn on that VLAN on all the switches. I turn the VLAN on in here, so the IP would be on this guy as well. I would shut it down here, and then I would advertise it into the network here, and then the edge would learn it through BGP. And we're going to see what that looks like when we go to configure VXLAN in the data center at the HQ location. But that's how I would go about doing it. And then I would start moving away, and then eventually anything that was on switches over in DC3, I would pull them out, and then they would be replaced with Cat 3 or Nexus 3Ks. So my goal was to have the spine Nexus 9Ks where it made sense, 100 gig backbone, and then I would have a couple of 100 gig or whatever the uplink capability is of the Nexus 3K. I would connect them to the 100 gig, so I would move my backbone from 10 gig to 100 gig, and then use overlay VXLAN encapsulation to do the migration. And so when I walked him through that was complicated. It was over his head. He could not comprehend how to do that. And at least the first time I explained it to him. And once I went and whiteboarded it again for him, I think it started to click, but it was still a monumental task to try to get everything off the old environment and onto the new environment. And I said, I understand that. But until you get there, you're still going to have the same problem. So I said the simplest way is to connect the old to the new, be a layer 2, and then shut down all the old SPIs. So shut down all the routing on the old. And then from there, I'll be able to move all the routing up to the new. So now that you're on Nexus as your gateway with the Anycast gateway, and then go from there, I'd be able to move that up. The border leaf would be your edge. All this in between here and here is BGP, and then it's BGP out to the edge. You run BGP there, and then from there you're able to get out to the rest of the network. So you'd still be flowing through the old until you're able to move all the stuff off the old switches and onto the new switches. That would take some time. And theoretically speaking, by having a 100 gig backbone, you'd still be able to stay connected to the old. You wouldn't have to move to the new until you wanted to. By having at least 10 gig links that were port channeled, you can run port channels down to the old switches and have a 10 gig uplink to the fabric through the old, and then when it was comfortable for the customer to do it, we'd swing the cables for them. Go in, move the cable, and we would do our best to try to put the switches in the same rack, so we wouldn't have to go fish them up through the plenum space to reroute the cables. So it was kind of a weird way of doing it, but it was a way to move them from point A to point B. And this is something that, like, when you think about networking and design and architecture, this is a migration plan, and it's a staged migration. It's not a flash cut where you're trying to swing cables over. Because here's the thing, with that much of port density and that many access layer switches, you don't do a flash cut with that. There's just no way. You got way too many things can go wrong unless you're doing per customer or per switch, and then you move or per VLAN. That would probably be how I would do it. Is I would move everything on a particular VLAN. That's actually what I suggested. I was like, you move it per VLAN, so that if there's a problem, all you have to do is move the cables back. It's a fairly simple move, and he was okay with some of it. Most of it he was not. But I actually stayed in touch with somebody that worked there for a while, and eventually they years after I brought it up and made the suggestion, eventually they ended up going that direction anyway, because they didn't have a choice. They couldn't the 6500s, they couldn't get the specific line card that they needed anymore, and I forget all that information. It's no longer relevant because the 6500 is a boat anchor now. It was a workhorse. It was a great switch while it was there, but for the use case that they were trying to leverage, not a good idea. But it's just one of those things where you take it as it comes, and this is one of those situations where you had to just deal with you had to play the cards you were dealt, and I'm glad that I no longer work there, because it was a nightmare to work with. But you don't grow as an engineer or an architect until you are faced with such challenges like that, and you have to work through them. Simple as that. So that's how that comes into play. I hope that explains it conveys the drive behind that, but it was one of those situations where you just have to, you take it on the chin and you continue working through it. So beyond that is pretty much what I wanted to talk about in this video. So let me go ahead and clear the screen. Let's scroll back up. So we have our subnet figured out, right? That's a good thing. And we have our VLAN ranges that we're going to go through. And actually, hold on one second. I need to make an adjustment here. So I'm going to put this in here. Put my pen tool back. I'm going to make this the 1300 range, because I told you I was going to do extended range VLANs. Let's go pull up this guy again. We're going to play around with extended range VLANs, and I'm also going to use manual VLAN pruning in this environment. I'm also going to be leveraging VTP to deploy them. We'll talk about how that works in the next video and how that comes into play. That'll wrap up VLAN technologies. And then what I'm going to probably do is once I get through VTP and we get the VLANs configured, then I'm going to jump down to spanning tree, then we'll jump to ether channels, and then I'm going to deal with switch administration, because we're at the manage the MAC address tables. Technically speaking, manual VLAN pruning is a way of doing that. The other MAC address table management is like the timers. You can adjust the timer. By default, it's 5 minutes. So if you wanted to make the MAC address timer shorter, so don't hold a MAC address in memory for as long, you can do that too. So, but one way or the other, we'll get through that and how error disable recovery works. If you have a link go down or there's an issue, you can unflap a link, things like that. So hopefully that was informative for you. I'm trying to keep this design, why don't do this, why don't do that, stuff like that. So if you guys have any questions, please leave a comment in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine people in the next video.